Okay. Hi, good evening, Nakirti. So, are you able to see my screen with induction motor? Anybody? Yeah, fine. So, you are looking at induction motor that is a squirrel cage induction motor which has 72 slots. You can see the slots here and 84 rotor bars here, rotor cage winding, what we know. So, this is cage winding, the yellow one, and the blue one is the rotor iron core. Let me show you the 3D view of the machine. So this is how some induction motor looks like. So if you see, yeah. So this is the shaft. This is visually, earlier it was visible, but not now. Not visible? Okay, fine. Let me see what is happening. Uh, hmm. I hope it would be visible now. Yeah, thanks. So this is a typical induction motor, which we will use in problem solving also, but it is very important to visualize the machine. I hope some. So till the software responds, so let me read the question, what it was given. So this was the question which appeared in 2016 for 1 mark. Here we have to calculate the torque produced by the motor, and this equivalent circuit was given. And this is two-pole three-phase induction motor here. Two-pole three-phase induction motor, and air gap voltage is given 210 volts. So you do not need to calculate air gap voltage, and everything you can analyze from the rotor perspective. So in this motor, a slip is also given. 0.05 of slip is given here, and we all know how to calculate power in induction motor. How it is produced? Can anybody tell me? Till then, I will check the software.
So formula
Formulae. You can speak formulae or anything.
3
Three.
into IR dash square into RR dash by S.
Yes, right. So S is slip here, and the power is developed along the that rotor resistance. So the higher the rotor resistance will be, the higher power. But one side effect of that machine is with higher resistance you will get higher losses. So that's why induction motor is considered as less efficient motor generally. So that's why people moved ahead with some advanced permanent magnet synchronous motors also. So that was the advantage because to generate torque, this you can see the cages here. Let me show you the cages. So these are the rotor bars which are placed along the, rotor lamination. So these bars are fitted in the rotor laminations, and here the current will be induced from the stator side. So this would be the typical stator slots you might be able to see here, and here a stator winding would be fitted. So this yellow one is the stator winding, if you are able to see, and the winding is wound in distributed fashion. So you can see how winding is wound, and if you want to see for single phase, this is how distributed winding is wound generally. Or you might have seen the linear pattern, so you can see how these linear patterns are wound. So this I wanted you to visualize. You may visualize here easily because generally machine is taught in theoretical manner. People are not able to visualize. So for that purpose, I am presenting this, and you can see more things like uh, shafts are fitted along the rotor inner hole or radius. So this is how a typical induction motor looks like. Is there anything more you want to know about this geometry, or is it fine? So I will move ahead with circuits and all. One more thing I wanted to show you how the flux path completes. So let me see. So till this will run, we will see the problem here. Mm, hmm. So this is the general circuit of any induction motor. Here, let me take the screenshot of this so that I will be able to explain. Hmm. So this was closed. This is supply that is, let's say, 170.9 volt of phase voltage supply, that is sinusoidal AC voltage. Some current will flow from the stator side. It will flow through the R1 resistance and X1 reactance, right? It will flow through that. This gray color is inductance or reactance you can call, and this white one is the resistance, right? There is some logic behind the gray color because of saturation in inductance or coil. So for that purpose, it is shown. And in rotor, generally R2 dash by S is equivalent resistance. That why do we divide by S to convert? We all know that rotor frequency will be S times a stator frequency. If a stator frequency is F, then rotor frequency would be S times F, that is slip, and S is nothing but the Ns minus Nr by Ns, right? So to bring all the circuit at same level or same frequency level, we do the transformation and we divide the resistance by S, and we bring X2 also as a function of F, not SF. Earlier it was SF, now it will be converted to F. Let me draw the circuit as well. Earlier, let's say V1 was there, R1, X1, stator leakage reactance is XL, and this is RC, core loss component of a stator. This is magnetizing inductance or reactance, and XLR, rotor side, and this is R2 dash by S. Okay, so here XLR is the function of F. Okay, otherwise, if induction motor is running at any NR, and NR is nothing but the NS into 1 minus S, and slip is the operating frequency, the original operating point of the parameters are like that. It would be J omega LR into S. Okay, S will be multiplied, and here S will be absence. And the induced EMF across the magnetizing inductance would be E2 dash into S. Okay, so to remove this or to get rid of this slip factor from each and every terms, we what we did earlier, the current was I2 dash is equal to S E2 dash. This is I2 dash. S E2 dash divided by under root. I'm simply applying a KVL, R2 square plus omega LR into S square. So this was current earlier, okay? Now we want to convert it to at same frequency, all frequency of F. So we will divide here also by S, here also by S. So for that purpose, if you simplify it, you will get E2 dash divided by R2 dash square, sorry, R2 by S dash square plus X2 dash square. We did here very conveniently, but later in advanced courses, you will get to learn that it is not done so easily. How will you divide just by S and you convert from the rotor frequency to a stator frequency? So you will get to know about some reference frames. So that is some another topic, but it is very convenient at this level that we divided by S and we are converting rotor also at the FS, a stator supply frequency level. Okay. Now, let me see the circuit here. So, you can see this motor has secondary, this is secondary side inductance, and the resistance is broken into two component. So, can anybody tell why it is broken into two component, or what is the inference of that? Why it is done so? We could have easily written R2 dash by S, right? So, has anybody has any answer?
Yeah.
Huh? Yeah,
One
no.
upper one is representing air power.
Hmm.
The power through upper one is air gap, and second one is for rotor.
Right, right. So, one component is for rotor copper loss, and one component is for mechanical developed power, right? So, we can always write R2 dash by S. We can always break R2 dash would be copper loss component. If you multiply all by I2 square, here also I2 square, R2 dash, the rest would be R2 dash by S minus R2 dash. Okay. So after air gap power, there is some flow of power. I think I should draw that as well. Some input power would be supplied from the stator side, some stator core loss, stator copper loss would be there. Then it will reach to air gap. Okay. After that, some losses would be there, and that is the rotor copper loss. After that, the power level is known as mechanical developed power. Okay. Or also rotor iron loss, you can say. And this mechanical power could be equal to shaft power or output power if the rotational loss is zero, but it is not generally. So rotational loss will be reduced from the mechanically developed power. So it is PM is nothing but the PG 1 minus S. Okay. And this rotor copper loss is SPG. So if you go from this side to this side, if you go from this side to this side, so if you add both PG1 minus S plus SPG, you will get is equal to PG. PG1 minus S is mechanically developed power plus SPG. It would be equal to PG. Okay, so we should always remember this power flow. Then you will be able to calculate efficiency, torque, power at any level. Otherwise, you will be confused which is mechanical developed power, which is output power, which is rotor copper loss, which is stator iron loss, copper loss, or input power. Okay. So if this power flow diagram would be in your mind, it would be very easy to solve any power related problem. So let me see if I am able to show you. Just give me 1 minute. I don't know what is happening. Okay, so I think in at last of the session, I will be able to show you some flux path in the induction motor. I wanted to show you right away, but some glitch in the software appeared. So for that purpose, I will postpone it to the last of the class. So, okay, fine. Hmm. So this was all about the circuit. And if you see this resistance R2 dash is, R2 dash into 1 minus S by S. So this is the resistance where mechanical power would develop. So you can see this resistance is higher and this resistance is lower. And this resistance value corresponding to the rotor copper loss. Okay, this is magnetizing inductance, so this is generally higher than any other inductance because this inductance is responsible for the flux establishment in the machine. That's why this inductance or reactance, you see its value is higher than the stator leakage reactance as well as rotor leakage reactance referred to the stator side. Okay. Ah, so I hope now I have that simulation. So let me first solve the problem here. What the problem was saying. So in this problem, we will solve it. We need to solve the torque, and torque in motor we all know how to calculate. We all know torque is equal to power by omega. Okay, this is a general formula which is applicable in all the machine. But here in induction machine, we have issue. Which power, which speed, either synchronous speed or rotor speed. Which power? Shaft power, air gap power, mechanical power, which power? So here also it is not mentioned explicitly that which torque you have to calculate. If it is not mentioned, you will always take as mechanical, mechanically developed torque, okay? Mechanically developed torque, and anyway, the rotational losses are not given. We will consider zero, so we will directly reach to the shaft torque. So whatever the mechanical torque would be developed, that will be equal to shaft torque. Now, this is rotor leakage reactance referred to a stationary side. So you can also see from this problem is also framed while keeping all the parameters in mind. So this value is lesser than this value. So this magnetizing inductance or reactance would be higher anytime. Now we know Vg, we have this parameter x2, and we have R2 dash by S. Okay. So to calculate power, we will easily do I2 square into R2 dash by S. Okay. So that's why I have done here. I2 I have calculated. That would be nothing but Vg divided by R2 dash by S, 0.05 divided by S, and S is also given 0.05. So 0.05 divided by 0.05 would be equal to 1. So that's why I have taken 1 here. This is R2 by S, R2 dash by S, and this is X2 dash. I have taken directly since it was given in the problem. Now, one mistake we always do, we do not care about the number of phases. Since it is given three-phase induction motor, we have to multiply with 3 I2 square into R2 dash by S. I2 we have calculated here. We will multiply with R2 dash by S, and we get here air gap power is equal to 126.19 kilowatt. That is air gap power. Now I just told you mechanical developed power would be air gap power into 1 minus S. If we add Pg into 1 minus S plus SPg, Pg into 1 minus S plus SPG, you will get air gap power. We have air gap power. We need to calculate mechanical power, and that with the value of S is equal to 0.05, you will get this value 119.88. Okay. Till here, any doubt? So I think it should be fine. Okay. So I should move ahead. Uh, we have calculated mechanically developed power. Now, to calculate torque, we all know this power by omega is equal to torque. Which power I need to take? If mechanical developed power we have, then we have to take the rotor speed. Okay. Why? Because when the power will develop, when the power will develop when rotor will rotate, and the speed at which rotor will rotate, that will give us the torque, right, corresponding to that point. So mechanical power by omega r, or air gap power, we know Pg by omega s. At air gap power is corresponding to a stator supply. So if you break it further, if you break it further, you will get Pg is equal to Pm by 1 minus S. Sorry. No. Pm is equal to PG into 1 minus S. This is corresponding to PM divided omega S. Omega R is equal to omega S into 1 minus S. This is corresponding to omega R. So again, the same ratio is maintained. So that is the beauty of this induction motor. If you calculate torque at, with this formula, PG by omega S or PM by omega R, you will get same value. So it is just coincidence. But you cannot say directly that it is developed torque or it is the shaft torque. Okay. So that you need to keep in mind. So let us move ahead. So torque, I did PM by omega R to calculate mechanically developed torque. If PM we would not know, if we would have that PG value, we will do PG by 1 minus S also. Some manipulation we have to do. And omega R we have calculated. Omega R is equal to nothing but omega S 1 minus S. And omega S is nothing but 2 pi ns by 60. Okay. So that value I did put here, and you can easily get the torque value, and it was the answer for that problem. So any doubt in this problem? This problem is solved here, and I am going to show you some flux paths of the machine. I don't know why every time it is getting disappeared. Okay. So this flux path, I hope would be visible to you. So you can see this six pole. How it is six pole machine? Because it is six flux paths completing, and the number of pole, the number of flux loop completed in any motor, that is equal to the pole number. So you can say it. Let me take the screenshot again. So this is one flux path completed, the other flux path completed. Okay. So how this flux path is getting produced by from the stator MMF, which a stator's windings are placed in the slots and rotor windings are placed in the slots. So if FF and FR, sorry, FA, so they would get interacted with each other. So torque would be equal to FA, FF sine of alpha. Let's say it is alpha. So this is how torque produced in any motor. So here these coppers are placed in this rotor slot, and this is how this machine is getting coupled with the stator RMF. So this is a stator RMF which is rotating here. So this is a stator RMF which is rotating here. I hope you are able to visualize. So it is flowing through this tooth and getting to rotor side, and further it is completing the path through the iron, since iron is the low reluctance path. So in this manner, it is completing its loop. So any problem in visualization of flux paths? And someone had asked earlier that why flux is needed. So this is the purpose why flux is needed in any machine. Without coupling of flux, we cannot rotate or we cannot generate the torque in the machine, right? So that is the basic philosophy behind that. And you can see let me show you some data also. So we provided supply from inverter. You all know inverter can provide three-phase supply. balanced three-phase supply I provided with the help of inverter. And you can see air gap torque is 108.94. Is it visible? The data is visible?
Yes, sir.
Fine. So air gap torque is 108.94 Newton meter and shaft torque is 107.11 Newton meter. So this much loss is happening from air gap till the shaft. Okay. And input active power was 77.23 kilowatt. Okay. And total input power, that is apparent power, would be the square of this plus reactive power. And output mechanical power is 72.9 kilowatt. Okay. And input electrical power is 77.23 kilowatt. So to calculate efficiency, we have to do the division of output mechanical power, that is 72.908 divided by input electrical power 77.23. So you will get efficiency of 94%. Okay. Input reactive power is provided 54 kVAR. Okay. This is input reactive power. And total losses which is happening, that is approx 4.3 kilowatt, right? So this is the some data where you can visualize that how much air gap torque, shaft torque, or output power, air gap power, input power. So just for the sake of that purpose, so you can I want to show you some loss data. So see, this 1.1 kilowatt is DC stator copper loss, means a stator R1 which was provided in this equivalent circuit. Let me show you this circuit. So this loss across this resistance is happening 1.1 kilowatt. Okay. And the rotor copper loss would also be somewhere placed. So yeah, this is rotor copper loss. It is 0.16 kilowatt. So uh, this is across this uh, lower resistance 0.001253. So this is across this resistance. And after moving across other data, so you can see iron losses are also significant, 1.2 kilowatt. Rotor iron losses are lesser than the stator iron loss because the stator is more saturated. You can see from the figure, a stator is more saturated than the rotor. Okay, because the stator had higher this blue point and 0.98 of magnetic flux density across that. So that is the reason behind that. So I hope we got the idea behind what is happening, what generally happens in induction motor. So I think that's all about induction machine from my side. Uh, if any final question you have, you can ask now. Otherwise, I will close this window and I will move on to next problem, I guess. So everything clear? This will be helpful if you move ahead, or if you want to, we just cram up all the formulae in machine. So you don't need to do that. You can see there are softwares nowadays which, which can give you more insights about that. Okay, fine then. I will move ahead. You can see also some graphs here. This is how air gap flux density graph. So this is also sinusoidal, almost sinusoidal. It would not be exact sinusoidal because in practicality some differ would be there. Okay, so that's it. Let me move ahead with other problem. Hmm. This is a basic question of circuit is also it has also some turns ratio concept of transformer. So we will see. So we have to calculate the input impedance, which can be seen from this terminal. And how do we calculate input impedance? That we will see. So, and the value, if you know the input impedance, then you can easily able to know the value of A and B. So in transformer, if there are one turns, this is how any transformer is generally connected. So let's say this is the circuit and you need to calculate input impedance. This is R1. This is, let's say, X1, JX1. Okay, equal to J omega L1 or L2 because it is secondary, so L2, let's say. Okay, this is inductance. Now, to calculate equivalent input and its turn ratio, let's say N1 and N2, N1 by N2. Okay, we want to calculate Z in this format. We want to calculate Z in this format. Okay, so to do that, what procedure we have to do, that we will see. Okay, we have to transfer this reactance to primary side. How will we do that? If, let's say, R1 is at primary side, there is no issue with R1, but X2 could be converted to primary side with some other notation, that let's say X2 dash, and X2 dash would be X2 into some turns a square. Which one? N1 by N2 or N2 by N1? So if we are moving from this side, we are moving from this side to this side. So to the side where we are going, that we will take on numerator, that is N1, and that side from we are going, that we will take in denominator. So that is the basic funda behind this question. You just need to do the transformation. Okay. Now we will see how to. Here two levels are there. First, we have to go from this level to this level. Again, we have to move from this level to this level. So I am solving for first level first. So here only R is there, that is 2.5 ohm. So let me draw the equivalent circuit. So if R will come here, 2.5 ohm, okay, and let's say R dash, R dash. Its value would be what? Can anybody tell me what will be the value of R dash? No value even in expression form A or B, anything. Not exact value if you are able to guess. So just now I said I will do the transfer. So 2.5 into some turns ratio a square.
1 by a square.
1 by A square. Correct. Thanks. So we are going towards 1 from A. So towards we are going 1 from A. So that would be the ratio. L is already there. So 1 millihenry. Let me convert it in terms of X. So X is equal to J omega L. Omega is 5000 radian per second into 1 millihenry. So it would be J5 ohm. Okay, so this I am changing here, J5 ohm. Okay, okay, fine. So we have completed one level. Now we will move ahead and we will try to shift this R dash and X towards this. Someone may say, why don't you shift this capacitor to this side? But that is not input level. Okay, input level is this, towards 1 is to B. So towards 1, that you need to take care. Okay, if you know to jump, you it doesn't mean you will jump anywhere. Okay, you have some fixed path. So now we will jump R dash and X towards input side. Okay, so for that purpose, R dash, that is nothing but 2.5 by A square. I think I have solved somewhere. So, okay, 2.5 by A square plus J5 into some turns ratio. That ratio would be, we are moving towards 1 from B by B square. Okay, so that would be the complete Z in. And how would it look like? Capacitor, inductor, resistor. Okay. This would be your Z in. We did not calculated the value of capacitance or capacitive reactance. So that would nothing but x is equal to 1 by j omega c. And that value I have calculated here already earlier. So this is the value of 1 by j omega c. J will go up and it would become minus j omega by omega c. And that omega was, 5000 radian per second, and c is 10 microfarad it is given. So it should not be any issue. And Z in also given, that is equal to 2.5 ohm. 2.5 ohm. Okay. We need to solve this equation, but here it is only one equation and two unknown A and B. So how will we go ahead? Uh, Indirectly, it is given that it is purely resistive because no inductive circuit or capacitive, means no reactance is present in the circuit. So it is solely resistive circuit. It means whichever component will have the imaginary component like corresponding to J, that will be equal to 0. So let me solve it for you. So I will multiply first these two terms. So I will get 2.5 by A square B square plus, after this multiplication, J5 by B square is equal to 2.5. Okay, fine. I think some mistake I have done here. I have left the capacitive terms, that was minus J20. So 2.5 minus J20 I have left here. So you need to also consider minus J20. So minus J20 is equal to 2.5. So this 2 is reactive component or imaginary component that I will equate is equal to 0. Okay. And this is the real component which I will equate to 2.5 because we can see this as this. Okay. So 5 by b square minus 20 is equal to 0. Then you will get b is equal to plus minus half. But we cannot take minus sign because it is, you know, uh, from the resistance and inductance side. So resistance and inductance both cannot be in minus. So for that purpose, B would be equal to half. And after solving this, we will solve this real part. 2.5 by A square B square is equal to 2.5. This will be get cancelled and A square B square will be equal to 1 and After putting b is equal to half, you will get a is equal to 2. Okay, I guess, yeah, 2 or something else. Let me solve. B square a is equal to 1 by b square. 2 only, yeah. So here a is equal to 2 and b was half, so it was in answers of option B. So we can choose option B. Okay. So any doubt in this problem? I hope it was simple, but if any doubt is there, we can discuss. So if no doubt, then let me go ahead with some other problem. One problem based on DC machine, but that is very simple problem. But since that problem was with me, so I have to discuss that. Huh. So you are able to see the problem, I guess. Question number 21. It also appeared in GATE 2016. Okay, for 1 mark. It is saying a shunt connected DC motor operates at its rated terminal voltage. Its no load speed is 200 volt, 200 radian per second, and its rated torque is 500 Newton meter. Okay, so no load speed means at no load means no armature current. Armature current is 0. Okay, so when IA is equal to 0, this 200 radian per second was the speed of the DC motor. At rated torque, its speed falls to 180 radian per second. Okay, so after loading any motor, this speed like falls. So this is general characteristics of this load. As load increases, so a speed falls. So that's why here this speed is 180 radian per second. This is a simple circuit of DC shunt motor. Okay, this motor is driving a load which load torque depends on its rotational speed. Okay, you all know motor torque does not depends on rotational speed. It depends on its current. Basically, it may depends on rotational speed indirectly, but here it has some given parameter. Its load torque is 2.78 times of the rotor speed. Okay, so that is saying in the problem. Now we have to calculate at a steady state what will be the speed of this motor when it is driving this kind of load, and the load characteristics is 2.78 into omega. Okay, so generally some motor is connected with some drive. Some motor is connected by the shaft. It is driving some load. Okay, so if this motor would rotate, so this load would also rotate. So it is the load characteristics, and we generally operate motor to move some load or operate some load, like fan or vehicle or something. In electric vehicle also motors are employed for that purpose. So that's why motor is there to drive the load. Now we know this load characteristics 2.78 into omega. The question was asking what will happen at a steady state with the motor. So we all know at a steady state, the torque applied by the motor would be equal to the required torque by the load. Okay. So this was very simple problem. That's why it was asked for 1 mark only. So we just had to equate it. TL is equal to TM, and TL is 2.78 into omega r, and TM we know 500. And after calculating it, you will get 500 by 2.78, and that would come out to be 179.85 radian per second. So at a steady state, when load torque is equal to motor torque, the speed of rotor of DC motor would be equal to this. Okay, so that was the answer for that problem. Any doubt in this problem? So three problems are solved today. Do you want to solve more problem, or should I discuss something from that simulation model, or should I discuss something else, or you can ask anything because we have 9 minutes of more time left. Okay, so Nakirti is saying no. And so, what do you want me to discuss? Anything? Anubhav, you want to say something?
Sir, question.
Question I should discuss?
Yes,
Okay,
sir.
okay, fine. Has a square. So I will discuss one problem based on three-phase transformer. I will try to wind up this problem very quickly so that you will be able to catch up your next class. I know on Thursday you have back-to-back three classes, so but you try to manage. It is a one-day thing. So okay. So this is the problem. You did the problem. Okay. So now Kirti is asking in one question, torque is given 70 Newton meter at rated parameter, but after solving current from given parameter, torque was given. So now Kirti, can you share the question with me? Uh, I will have to take a look on that. Okay. So if I may look at the question, then I will be able to tell you the answer. You can mail me the problem. I will give you my armature current word decision. Okay, I am writing my mail ID in chat box. You can send me that problem. I will take a look at that and I will discuss in next class. Okay, so anybody have any issue, you can mail me at this mail ID. So that I will take up the problem in next session. Okay, so let us move ahead quickly with this problem. This is based on three-phase transformer, and here we are required to calculate the full load efficiency. So we all know efficiency is equal to output by input. Okay, so output would be, you know, the percentage of loading into kVA rating of the transformer into cos phi. This is the output. Okay, anybody has any issue in this formula, then I expect that you know this formula, iron loss plus x square, because I cannot derive formula right now. If you say, I may derive this formula in next class, okay? So for that purpose, I will move ahead with the formula only, okay? So power factor is given. It is given as unity. This power factor is unity, so it will be 1, okay? Now, in problem, it is connected delta star. And 3 is to root 3 kV, 50 hertz transformer, typical. KVA rating is given okay, and the full load efficiency. So if the percentage of loading is mentioned in the problem, we can take loading as 1, okay. So this is 1. KVA is also given, that is 900. We need to calculate iron loss and copper loss, okay. So for that purpose, I want it to solve the problem on the basis of per unit. So let me solve it. Copper loss in per unit is equal to RPU. That is the resistance in equivalent resistance in per unit, and per unit resistance is equal to R given by mod Z base. Okay. So for that purpose, uh, and I guess iron loss is given in the problem. Okay. So iron loss was 10 kilowatt is mentioned in the problem. The rest I have to calculate this copper loss, and copper loss we all know is equal to RPU. Okay. Now the entire mission is to calculate copper loss here, and we will move ahead with, we will take some base value, and base is nothing but the KVA rating of base will be 900. Okay. And some voltage. So voltage will change, since we, from a star side the voltage would be in a star format. So V base would be equal to root 3 kV. This is line value, and here it is phase value 3 kV. Okay, so it is base. So if you are in this zone, you will take this base. If you are in this zone, you will be in this base. Okay, but we have this, we will have some resistance here and some resistance here. So we will try to refer from secondary to primary. Okay, so first we will calculate Z base, and then we can divide it with any other resistances. So to calculate Z base, we have some voltage square divided by EA. So the dimensionally it will become V by I, and it will give you impedance. So KV square is, let us take from a star side. So if you take from a star side root 3 kV, root 3 kV square divided by kVA was 900 kVA. So 900 kVA, and if you solve, so this will come out to be 10 3 into 10 raised to power 6.9 into 10 raised to power 6 VA, and it will be equal to 10 by 3 ohm. So that is your Z base. Okay, we have calculated Z base. Any doubt in this part? Since I am moving fast, I am expecting that you are getting it. If you have any doubt, you stop me in between. So the next task is to calculate RPU. Okay, resistance per phase on high voltage side is given, that is equal to 0.3 ohm. So R1 is equal to 0.3 ohm, and R2 is equal to 0.02 ohm. Okay. So R2 is 0.02 ohm. This is given. R1 is fine. Okay, but this all data in ohm actual value we need to convert in PU. So R1 PU will be equal to, so you need to convert either from delta to star or star to delta. Okay, so it is always better if you take any one thing reference and you stick with that. Okay, so let us take, I am taking a star as a reference because that is very simple one. So I am taking a star, so I will transfer this resistance to secondary side. So R2 would be fixed. So R2 PU would be fixed. I am not transforming that. It would be 0.02, and base was on that side was 10 by 3. Okay, so that would come out to be 0.006 pu. Now, I will manipulate R1 towards the secondary side, and that would lead to, you know, because R2 we have calculated, R1 actual value is given zero point 0.3. We need to convert first to secondary side because we are going to secondary side. Let me call it a star side from delta side. Okay, so we will solve it. The turns ratio also we know. In a star side, it was root 3 kV. It was line value. Okay, so what would be phase value? That will be divided by root 3 in a star. Okay, and delta, it was 3 kV, and in delta phase value is equal to line value, so it was 3. So we have referred it to secondary side, so the value which will come, that I have noted here, and it would be 1 k 1 sorry 1. Okay, I will solve it here. This will cut, so 0.3 divided by 9, so 1 by 30. 1 by 30 would be per unit value of R1 dash PU. Okay. We have R1 dash PU, we have R2 PU. So we will add both. And I guess I haven't divided it by base value. So base value, after dividing it with base value, then we will get per unit value. And this value will come out to be 0.01 divided by 10 by 3. Okay. So then you will get 0.01. So total per unit value R1 dash PU plus R2 PU is equal to 0.01 plus the earlier one was 0.006. So you will get equivalent 0.016 PU. So this is equivalent R1 dash PU. Sorry, R equivalent in per unit, and that will be equal to copper loss in per unit. Now you want to convert it into kilowatt. So either you can convert it in kilowatt or you leave it all in per unit value. It doesn't matter. So if we have calculated everything in per unit, so why not we go ahead with this? Okay. So in efficiency term, where I have written that I will put all things. So here I will put all things. X was 1. KVA, let us take 1 because it was rated per unit. Power factor was 1. Okay, fine. Output is 1. Now losses. Iron loss was 10 kilowatt. So 10, let us convert iron loss also in per unit. So PI in per unit would be 10 divided by 900 because 900 was KVA, and it will be 1 by 90. 1 by 90 plus copper loss, we just calculated 0.016. Okay, into x square was 1, so 1 square. And after solving this expression, you will get some value, and let me tell you that value. That would come out to be, you know, after solving this expression, you will get 0.973. Okay, this is your efficiency value, and if you calculate in percentage, you have to multiply with 100, and that will 97.3%. Any doubt in this? I know I went fast, but I hope it is okay. If you have any doubt, I can also discuss in next session. But if any doubt, instant doubt, I can tell you now. So that's all from my side for this session. Okay, thanks, Nokirti. And I hope it is fine with everyone. You can join the next session, I guess. Yeah. Thank you. Thank you, everyone. Bye. So I'm winding the session.